Okay, this video is going to be a little longer than the last two on this third video on data and distributions, because now we're talking about a little bit more complicated and technical case. I'm going to try to take it kind of slow and walk you through each step, but this is the grouped frequency distribution and the grouped frequency histogram. And while the example we're going to have may seem ridiculously easy because you can just see what the categories are going to be, I'm going to take you through how to formally calculate what the categories are going to be, what are called the class interval limits, or the class limits. Because I think doing that with a simple example, hopefully you would then be able to understand the concept well enough to then generalize it to real examples or more complex examples. So in the previous video I introduced frequency histograms. In this video I'll assume that you've seen that one and the one before it about frequency distributions, so that both of those terms are at least somewhat familiar to you. There's going to be a lot of new terms in this video. The only good thing I can tell you about that is because it's a video, you can replay it if you need to. Now we're going to talk about a slightly more difficult case where the raw frequency distribution is not helpful. And this can happen for lots of reasons. For example, when the variable we want to summarize and describe is actually a continuous variable. Because in that case, no two values of the variable are exactly the same, at least if your measurement precision is adequate to measure a continuous variable, then no two values are exactly the same, so the frequency histogram is next to useless. Instead, we use a grouped frequency distribution and grouped frequency histogram to get an idea of what the data looks like. Alright, so here let's just use an example. I'll use an example from psychology since that's my field and what I'm most familiar with. But you could substitute any variable you want there for agreeableness. You could substitute fixed income in thousands of dollars, or I don't know, whatever. Number of arrests per month, whatever your field is, you can substitute for that variable. It kind of doesn't matter what the variable is. Suppose we measured a personality trait like agreeableness in a sample of 13 people. Here again, my made-up example is so small that you can probably see just by looking at the raw data some of what's going on, but that's just so you can make the connection between the raw data and the summaries that we're going to do. In real data, of course, it wouldn't be so easy. Anyway, the first thing we should probably do is something called the order statistic, which is just a fancy word for sort the data. So there's the order statistic for you, right? So now you've just got your data. You notice that the person variable, which again, remember, is a nominal variable, so those numbers under person mean nothing. They can be replaced by letters, by names, by arbitrary symbols. They're just sort of placeholders to denote there's an instance of something here. But the numbers themselves mean nothing. But you see that those numbers are now scrambled because the agreeableness numbers are now in order from smallest to largest. And this looks much better. Now you can really see in the raw data exactly what's going on. Again, you see that most people are in the middle, a few are extremely agreeable, and a few are extremely disagreeable. But to represent these data in a useful way, the frequency distribution and frequency histogram turn out to be terrible. Here, have a look. So remember, to make a frequency distribution, what we're going to do is just denote all of the possible values that our variables can take, and the frequency with which we observed each of those values. And you can see here that for 1 to 15, there was only 1 of most observations. There was 0 of a few. Oh, here, let me turn on my laser pointer. I always forget to do that before I start the video. There we go. Okay, so for a few of these, there's 0 observations, right? And for just a couple of them, there were 2 observations of that value. But for the most part, it was 1. And you can see that another thing that jumps right out at us is that our frequency distribution is actually longer than our raw data, because we had a potential for up to 15 observations, 15 different numbers in the range of our data. Some of our observations came out to be 0. So this is pretty terrible. And the frequency histogram is terribly ugly, right? Look at that terrible thing. That's just, ugh. It looks like somebody's bad bottom teeth or something. That's an ugly distribution. So we want something that will be more useful to us in summarizing the data. We certainly wouldn't want to show, if you're doing a data analysis for a client, you don't want to show your client that. That's terrible. All right, so instead, we're going to group observations into classes. So the first step is to decide how many classes we want or we need to summarize the data without losing too much information. I should mention here, whenever you summarize data, you also lose information. Of course, your data has a certain amount of information. There's a certain amount of information in all of these numbers right here. And anytime you're going to summarize all of these numbers with some lesser amount, some fewer numbers or something like a histogram, you're going to inevitably lose some of the information that's in there. And you want to balance that information loss against the gain in summarizing important things about the data. So we got to decide on how many classes, and for these data I've actually made up the data so that they will nicely fit into 5 classes. So you can probably see intuitively which values each class is going to have, but I'm going to show you how to formally calculate the value of each class once you've decided on the number of classes that you want to use. I do it with this very simple example so you can understand it, but the rules I'm going to show you work for any data, even for continuous data. All right. So once we have a number of classes that we want to use, we have to decide which values to include in each class. And again, you can probably see from the raw data that we're going to have a class that goes from 1 to 3, another that goes from 4 to 6, another from 7 to 9, one from 10 to 12, and the highest class is going to go from 13 to 15. But in the continuous data, or data that doesn't go from 1 to 15, it wouldn't be so easy to decide. And the software that is in reality going to decide for you often sometimes creates, well, I would say often creates, just terrible histograms. So I'm going to show you how to do it in the formal way. Even if you never have to do it that way, at least you'll understand better how your software is doing it, or at least maybe you'll understand why your software sucks at it so badly. All right. So first step is to determine the real range of your data. Now, what do I mean by real range? Well, let's just remember the range. So range, that's just the largest minus the smallest datum. But what is the real range? Well, the real range is the range of continuous numbers that would round into your data. For example, in these data, our precision is 0 decimal places, but imagine that we could actually measure with 1 decimal place precision and then just rounded those numbers. What if we measured a 0.9? We would round it to 1, right? So what's the smallest number that we would round up to 1? Well, if you remember your rounding, you'll remember that it's going to be 0.5, right? A 0.49999, we would actually round down to 0 if we were rounding to the nearest whole number, or nearest whole digit. But a 0.5 would round up to a 1. So the lower real limit of our data is 0.5. And really, finding real limits is really just the same thing as rounding. All right. So the first step is to determine the... Now, what about the upper real limit? That's where I meant to go with this. What is the biggest number that we would round down to 15, our biggest observation? Well, that would be a 15.5. 15.5 would actually round up to 16, so 15.5 then becomes the upper real limit of this class, or of this datum. So our real range is then just going to be the upper real limit minus the lower real limit of our data. So the upper real limit of our largest datum minus the lower real limit of our smallest datum. Okay, and so our real range in this case is going to be 15, the real range in the data. So the next step is to determine the class width, or class interval size. The class interval size is just going to be the real range of the data divided by the number of classes that we want to use to span that range. Now, when I teach this to students, they often get confused here. Wait, where did the number of classes come from? Well, remember back to like 4 slides ago. The number of classes is something that we decided on. Where did the 5 come from? I decided on it. I could use 4 instead, or I could use 6, or I can use really any number I want. But the math would get much harder with anything that doesn't divide evenly into the real range. Since my real range is 15, I'm going to use 5 because that divides nice and evenly into 15. that tells me that my class interval or class width is going to be 3. Easy, right? All right. Now that we have the class interval, we can construct our classes. You can start from the highest class and work your way down, or you can start from the lowest class and work your way up. I'm going to start from the lowest in this example. So what is the lower real limit of the lowest class going to be? Well, it's going to be the same as the lower real limit of the lowest datum, because that's going to be the lower real limit that would of anything that would actually fit into the observed range of my data. So now our lower real limit for that lowest class we know is going to be 0.5. Now what is the upper real limit of that class? Well, to figure that out, all we have to do now is add the class interval to the lower real limit for that class, and that will give us the upper real limit of this class. So we're going to add 3 to the 0.5, and that is going to give us our upper real limit on this class of 3.5. And so that gives us our apparent limits to the class, and these apparent limits are what we would actually show if we were to present a table of this grouped frequency distribution. So now you can see why this class has to be from 1 to 3. And by the way, these labels for the class use that the label for the class uses the limits that match the precision of our data, which are called the apparent limits. So the apparent limits of this class are 1 and 3. Now to get the lower real limit of the next highest class, it's super easy. It's just the upper real limit of the next lower class, or of the previous class. So to get the lower real limit for my next higher class, I just use the upper real limit of the previous class, or lower class. And so that's going to be 3.5, right? Just take the upper real limit from the lower class, move it up to become the lower real limit of the next class up. And now, how do I get the upper real limit of this class? Remember, I just take my class interval and add it to the lower real limit. And that's going to give me the upper real limit of the next higher class. And now, round up from your lower limit, round down from your upper limit, and you'll get the apparent class limits. All right? So now you can see why that next class has to be 4 through 6. So now we're going to continue in this way. So what you could do right now, if you think you get it, even if you think you don't, try it out anyway. Stop the video and try to get the next class up. And then restart the video and see if you got it right. All right, did you stop the video? You didn't stop the video, did you? All right, well, let's go on. So we just take, again, the upper real limit of the next lower class, move it to the lower real limit of the next higher class, and then add the class interval to get the next upper real limit. And there we go. And then round up the lower real limit, round down the upper real limit to get the apparent limits of the class. All right. Try it again. Stop the video and do the next 2 classes. They'll be the last 2 classes. We only have 2 more classes to go, right? We were going to use 5 classes. We've already done 3. Stop the video. See if you can figure out the next 2. All right. I'm sure you all did that. I'm sure you all stopped the video. Let's see if you got it right. All right. There you go. So again, we're going to take the upper real limit of the next lower class, move it to the lower real limit of the next higher class, add the class interval to get the upper real limit of that class, and then round up from the lower limit, round down from the upper limit to get the apparent limits of the class. Do that again, and here we have now our classes that we can use to group these data into a meaningful grouped frequency distribution. Now, of course, again, I know that this is a ridiculously easy example in terms of the data, and you could just see what the intervals were. Why can't you just make them up? The point here, again, is that just making it up wouldn't work in more complicated data, like continuous data. But this method will work for any data, even continuous data. All you have to do is go one more decimal place of precision than the precision of your measurements to get the real limits and real range, decide on the number of classes you want, and there you go. And of course, computers do this for you these days in real life, but you should understand how they're doing it, and you should understand when they screw up. For example, SPSS, a very popular statistical package which I use all the time, but it does not routinely do a good job of dividing these intervals, and so its frequency histograms are often very screwy. In fact, SPSS often does not have equal interval widths for its different intervals. So it'll have like a 1 to 2 and then a 3 to 9. I mean, that kind of weird stuff that SPSS does. I'm exaggerating a little bit, but not really by much. So you need to understand when your software is being screwy, and sometimes you can take control of that, sometimes you can't. Okay. From here, it's just a simple matter of counting the number in each class and putting that into the frequency column. Oh, and of course, when we do this as a table, we don't usually include those real limits that we used to build the classes. So when we create the table, we're just going to present the apparent limits. So here's our grouped frequency distribution table. So we counted up the number that fell into the interval 1 through 3. There was only one of them. In the interval 4 to 6, we had 3 of them fall there. In the interval 7 to 9, we had 5 observations there, and so on. 3 from 10 to 12, and only 1 from 13 to 15. So here you can see this looks quite a bit prettier than our raw frequency distribution looked. And now you can imagine the histogram for this, right? So to do the histogram, again, we're just going to put our classes on the x-axis. We're going to have frequency on the y-axis, and we're just going to draw bars for each class up to the frequency of that class. And you can see here for 1 to 3, we just draw it up to 1, and so on, so that you get the grouped frequency histogram. Fantastic. Now, something that I realized I forgot to mention when I did the video on frequency histograms is why the gap here, and what is the deal with the gap? Sometimes there's a gap, sometimes there's not a gap. What's the deal? Well, there's no hard and fast rule, but there is kind of a guideline for this, sort of a tradition, you might call it. And the tradition is this. If your measurements are continuous, then in your histogram, make the bars touch. No gap between bars for continuous data, for representing the frequency histogram of continuous data. But if your data are categorical or discontinuous, then put a gap in between the bars. And that represents that these are, in fact, discrete classes, that there's nothing in this interval here. Okay? So, just a little statistics tradition for you there. All right, that's it for this video.